So I'm going to go over a few of the templates from the standard template library. And the first one is generally when you go over the data structures, the stack is probably the easiest one to follow. So in this case, in order to use the standard template library from C++, you would say include the template you want. So we'll say include stack, and that brings in the stack for us. And now we can make stacks of anything we want. So in this example, I'm going to make a stack of integers, and I'll call it SI. So then I have some code here that basically I will start reading integers as input until somebody types in a -1. And then of all the numbers they put in, not counting the -1, the -1 is my way of saying no more input. They'll stack them up, and then basically I'll go through the stack saying as long as the stack is not empty, I'm calling the stack function empty, which I got from the stack template. It's a template class. It has a function called empty. And as long as it's not empty, I will keep printing out what's on the top of the stack. And then some of the functions you'd want to know what they're doing. For example, top will return whatever on top of the stack. It won't delete it. It'll just say, here's the top, and leave the stack the way it is. If you ask for top 10 times, you'll get the same top of the stack 10 times. It won't pop away the stack. The pop method removes what's on the top, but doesn't give it to you. So you might be used to the idea of a pop taking what's on the top, giving it to you, and removing it all in one step. And they decided to have top and pop be two separate operations. A really good website to know what these functions are for each of these templates is a website called C, the letter C, and then the word ++ spelled out. So CPLUS.com. They have a great website for not only the standard template library, but anything to do with C++. Okay, so if we were to run this code, if we were to compile it,
Should we copy this over or directly?
you could copy these all over after. I mean, they're all just like code snippets that kind of, I try to keep them small just so that they get the idea across. And from this directly, we want to run out. So it's asking to enter integers, and then I'll just put in 2, 4, 6, 8, and then I want to close it with a -1. And then the code prints out whatever I put in, it printed it out in backwards order. So it just stacked up the input and then printed them out in backwards order. So the idea of a template and having a type as the parameter, like I said, integer here, means we could use stack to do stacks of other things. So just a quick little demo that it's not just stacks of integers, it can be stacks of strings. This is almost identical code, except that it's asking me to type in words, and the words will come out backwards.
Why do you have to include string?
Oh, that's a C++ thing. So string is not a type that is given to us directly by the compiler.
Oh, really?
So in C++, we have to actually include string. Okay, and then so now I'm typing in words until I type in the word stop. It'll stack them up and then print them out. So other than that, it's basically the same code. So all I'm really demonstrating here is that because we can generate the type along the way, and then if I run this code, so what sentence should I type in? That'll print out backwards.
Use a palindrome.
Like what?
Race car.
Race car.
Race car?
Yeah.
Well, then it'll say car race, but, okay.
Yeah, we'll say race car.
What?
I said race car, it's palindrome.
Well, I might miss that.
Well,
It doesn't print the characters
Yeah.
backwards, it prints the words.
okay, so what this stack of strings was doing, basically, whatever sentence you type in, it'll, with the exception of stop, which is my way of saying the sentence is ending, it'll print the words backwards. So it stacked, it put race and then car on top of it, and then when I said stop, it then started popping off the top of the stack and printed out the words backwards. So hardly any difference between this code and the last one, except that we did string, int became string. We had to include string also. The parsing of the input had to change a little bit, and the output was exactly the same. We're printing the top and then popping. Nothing changed there. So really the type didn't matter much. It's the idea that we're using a stack and we're creating a stack of whatever we want to create a stack of. So what other templates are in the standard template library?
If you want to use integer, you wouldn't have to say pound include integer, right?
Right, because integer was a primitive type. That comes with the compiler. And C++,
String is-
characters come with the compilers, strings were added later.
So you want to make a variable string,
You'd have
Chris,
to,
you would have to literally say pound include string.
yeah, and then you could use the string class. You could also make strings out of arrays of characters.
Okay, that'd be normal.
But yeah, most people would use strings too. So then, another just interesting side, this might make sense one day if you have you're taking large inventory of data. So you can, there's a type called Bitset. This also exists in Java's collections. And basically what we're doing is we're dedicating one bit to something. So you could kind of think of this as an array of booleans. But if you do an array, a boolean takes up 8 characters, believe it or not. It's just a yes or a no. And I think in Java it takes up 16 characters. I forget exactly how much space it takes. But if you want to take up just one bit for something to be a yes or no, and if you had tons of things you wanted to dedicate one bit to, you could create a bit set. So that's the new template that we're using, the new parameterized template we're using here. So basically I'm creating a bit set, and it takes in one parameter, which is an integer. How many bits do you want? So it's not a type, it's just a bit, it's just yes or no. And from 0 to n-1, it means something to you. So now I'm saying I have 4 bits, and I'm calling it like a deck of cards. I could have made it 52 cards, but I just want it to be 4 cards. And then I have a function called set, which turns the bits on. There's also functions that turn the bits off. And there's also functions that say, are they all on, or is at least one of them on, are they all off? Questions we could ask about the bits. So at this point I set, well, what I originally did was I set all 4 bits on, but then I decided to comment one out so they wouldn't all be on. So now there's a function called size that'll tell us how many bits there are. There's a function called any, which will be true if any of them are turned on. There's a function none, which will be true if none of them are turned on. And if you go to that C++ website, you'll see all the functions. There's not too many, but all the things you could do with bit sets. So and then this code, I'm basically iterating. I'm using an integer as an iterator, which I can do, but a little further example will have a more interesting iterator. Right now I can use an integer to just go from 0 through less than 4, 0 through 3, and just add 1 to it. And then I'm basically printing out the bitmap, whether they're zeros or ones. And then I'm just doing a little exception code here. I'm basically saying if the count of the bits, the number of bits is, so count would be the number of bits that are currently turned on. If count is less than the size of the bits, how many bits there are, that means at least one of the bits is off. Then I'm going to throw an exception. So I created an object called a not full deck class. So when you throw an exception, you can create any class you want and then just throw that object. And what I'm doing is I'm saying if I don't have all the cards in the deck, I'm going to throw an exception that says you're not playing with a full deck. So a little code snippet like this could be used in a, let's say you were writing some software that had 52 cards in a deck, and your software is the dealer deals out cards to players, and you play a game, and then all the players have to turn their cards back in. You might want to check are all the cards in here. You might want to have a bit for each one and go through them all to make sure all the cards are there. And then if all the bits are on, that means you have a full deck. And if the software didn't return one of the cards, you know you shouldn't be playing the next hand because you don't have a full deck. So it's something like that. So the output of this code would be what? The size of the bit set should be 4. Are any of them turned on? 3 of them will be on, so that should be true or 1. Are none of them turned on? That should be 0 or false. So it should be like 4 true and false, or 4, 1, and 0. I forget how they say true or false. And then we're going to go through them. It should say 0 is set, 1 is not set, 2 is set, 3 is set, and then we should get the exception that says you're not playing with a full deck. Because the count, which should be 3, is less than the size, which is 4. So this
Why don't they just make new compilers that have strings in them? That really bothers
yeah, that's
me.
true.
That's something that everyone uses.
Bitset. Okay, run this. That doesn't ask us anything. So here's, here ends up being the output.
Good luck with that.
So this is saying the size is 4. Are any of them turned on? That is true. So 1 means true. Are none of them turned on? That's false. And then here's our map. Here's our bit set. The 0, 1 is on. This first one, the number 1 is off. 2 is on. 3 is on. And then we did get the message that says we're not playing with a full deck. So there are, just a reminder of how exception handling works, there are exceptions that come with the system, and then you can make up your own exceptions. I just created a class up here called not full deck, open paren, close paren. So it's a class that has no data, no methods. But I can create an object of it, which is an object that does nothing, and I can throw that object, the not full deck object, and then the exception handling will read it and go, oh, I know what to do with that. It's a not full deck object. And play that. Okay, so we have a template in the standard template library that is a collection of bits. And again, you could have made an array of booleans and done the same thing. But this will take up 1/8 as much space. So that's really why that's been added. Okay. Another popular data structure is the double-ended queue. So basically this is some parsing stuff we saw a while ago, just string parsing. We're adding, we're adding the DEQUE, which is pronounced deck. We're adding the double-ended queue. So that's basically an order of objects where we can walk from left to right and put things, put and pop things off of each end of the structure. So I'm reading in Word, so it looks like I brought in string again, so I'm reading in strings. And then I'm actually reading in character sets of up to 256 words. This code right here is not really the point of today's talk, but this is for parsing strings, to go from the beginning of the word to the end of the word, to cut up everything into words. Then take those words, the substring from the first letter to the last letter, and push that onto the back of the double-ended queue. So basically, what this code is doing is reading in a sentence and pushing the sentence onto a queue. And then we have the ability, if we want to, okay, so I know this is more of like a topic from a data structures class, but a double-ended queue, you can push things onto the back of the queue, and you can push things onto the front end of the queue. You can build it out if you want, and you can push and pop off of either end of the queue. So what this code is doing is saying, now that I've taken this sentence and built a double-ended queue that kind of goes from left to right, or from the beginning to the end, and put the words in the order in which you type them in, I'm now printing them out by saying, while the double-ended queue of strings is empty, is not true, while it's not empty, I will print off the front. So front is a function that we inherited from, not inherited, that we took from the double-ended Q template. I'm going to print off the front, and then I'm going to print a space, and then I'm going to pop off the front. Then I'm going to say, the next thing is, if the double-ended Q is still not empty, then I'm going to print off the back and a space and then pop off the back. So I can print from the back and I can pop from the back. So what is this output doing? So if you were to type in a sentence, what would its output be? So it cuts up your sentence into words, puts each of those words as one unit onto the double-ended Q, and then starts printing the beginning, then the end word, then the second word, then the second from the end.
So it's start.
So like this is something you couldn't do with an array, but you can do with a double-ended Q. So it's now printing the first word, then the last word, then the second word, then the second last word, and so on. And you can do this for all the words. So you could kind of you could check if there's a palindrome by saying, does the first and the, if we said, pop the front and pop the back and check that they're equal, then pop the front and pop the back, check they're equal again. So a double-ended Q is a good thing to check for a palindrome. But the way this is coded up is just demonstrating we can do things that you couldn't do with just standard arrays. With the double-ended Q, we can print from the front and the back and so on. So if we ran this code, this is double-ended Q. Okay. So if I run this, it's asking us to type in a sentence, and whatever we type in, the first word will come out first, then the last word, then the second word, and so on. So, is there any race car, palindrome?
Just do race car, but do spaces in between, right?
Race car with spaces?
Yeah. Oh.
So each one is counted as a string, each letter, in other words.
So you,
I could just
Yeah, just do
Well, now it's, so then it's going to say, so then it's going to say RR A. Oh, okay.
Yeah.
So if I say that,
yeah.
Yeah.
and how do I stop this thing? Okay. So it came out as RRAACC with the E in the middle. Because just basically the way I coded up the output. You could say anything where the meaning would change, like,
Nurse has 5 chips as well.
what's that?
I just Googled a palindrome. I got it.
So what would the output of this be?
Wow, nothing. You have to execute your program.
Oh, right. Command not found, right? Oh, let's stop this. Okay. Well, that was a good trick question, right? All right, so what's the output of this? I'm stupid with you. Yeah. Whatever. So you kind of get the idea, right? So basically, we can load stuff into this double-ended queue, and then, so the idea, now that you're starting to get the idea of what these structures are that are out there for us to just grab and use, you'd start thinking, what problem would I need to solve? If so, I should pick a structure that can do whatever it is I need to do. So, for example, if you wanted to have a structure of stuff and you needed to randomly shuffle them, then you got to go find one that does a shuffle. If you want to sort things, then you have to find some structure that has a method called sort. So different structures are used for different reasons. You got to figure out what it is you're doing. Then, of all the structures you know about, pick the best one and use that one. So let's see. So another structure is really a single-ended queue. But one thing I didn't do with this double-ended queue is I didn't walk through it. And walking through a structure, I think, makes sense in this case. Okay, so, and this is something I could have done on the last one. The double-ended queue, we loaded up the double-ended queue and then just read from the ends. If we wanted to, we could have started at the beginning and walked our way through and go searching for something in the middle without popping off the ends. We could do that. But in order to walk through a structure, you have to add something that is in this example. So for example, this is now not a double-ended queue, this is a standard list. So a list is a collection of data that is they're organized in a row. So there's the idea that you can start at the beginning and then go to the next item and the next item and the next item. But they're not necessarily like an array. They're not next to each other in storage. Every node has a way to get to the next node, but it doesn't have to be right next to it in storage. And what's going on in C++ behind the scenes is one of the node that has the data also has a pointer in it which points to the next piece of storage. So you might think, why wouldn't you just use an array? Why would you use a list? But an array, you have to know how many items you have at the beginning, and then you have to know exactly where they're going to be located, and as time goes on, if you wanted to insert into the middle of an array, you would have to take all the elements at the point where you want to insert and copy all the ones after it one notch over to make room. With a list, you can just randomly pick a new piece of storage, store the new data in, and then say, this item now has this one as its next, and the new one has the last one as its next, and you've added it very simply. So there's a trade-off between lists and arrays when you use one over the other. But this is yet another thing that we get to use, a list. So now we're going to have a list of strings called ls. Now what I want to do in this case is I want to go through the list. So now the question is, how, you know how like when you do a for loop, you have, usually they pick the variable I, which is the first letter of the word iterator. You use I to start at the beginning, you do something, and then you do I equals I plus 1, or I plus plus, to go to the next one. And what that does is, since I is an integer, it just adds 1 to it, which now refers to the next one. In this case, we don't want to add 1 to refer to the next one. We want to do what to get to the next one?
Find the reference.
Yeah, we want to, so there's kind of a function we have to do. We have to look at our own storage, ask ourselves which field is the pointer to the next one, and then load that address into the iterator to now say the iterator is now pointing at the next one. So it's going to turn out the thing we're going to use to iterate ends up being a pointer in C++. So we'll create an object called a list iterator, and then we'll say this iteration should start off by pointing at the beginning of the list. So the list will have a function called begin. I was going to say something like begin. So it's a function called begin, and that will return the first element of the linked list. And then we'll be able to say, let's go to the next one. Now the next one doesn't mean add 1 to the pointer. The operation plus plus is now going to say, look at the storage of the current node, find the next pointer field, whatever they decided to call that, and then make the iterator point at that field. That's what the plus plus will do for a linked list. If it was an integer, it would add 1 to it. But if it's a linked list iterator, it resets the pointer to the thing that's being pointed at's next field. So how do you do that in C++? You overload the plus plus operator. So whoever created this class, and these classes, they were created by a group of people, some from IBM and some from Hewlett-Packard, and then about 4 or 5 companies get together and write these templates. Whoever was assigned the list one had to overload the plus plus operator and describe its code, saying take the pointer, get the next field, set the iterator to point to that one. And there'll be code like, if next field is null, then we are at the end, so don't go to the next field, or set it equal to the end function, something along those lines. But somebody in this class said, if you are referring to a list string iterator, if this is the object that we're using and you do a plus plus, go to the overloaded plus plus operator. Yeah?
But that's only for the IT object, right?
It-
If you were to have like an integer and we put, say, plus plus, it will increment?
It's based on whatever the type of this thing is.
Okay.
So right now, if they didn't overload the operator and you called a plus plus, the compiler would say, I don't know how to do a plus plus. I don't know what this thing is. I don't know how to do a plus plus on it. But because they overloaded in this class, list, so they created a class called list with a T, right? Well, I'm sorry, it's C++. They said template class T, they probably used T. And then they said list T, it said class list T, and then all over the place, everywhere there was a T, they did something. Then they had to have overloaded the plus plus operator for, they created a subclass called iterator, and in that one they described how to they wrote an overloading of the plus plus operator. So now, if anyone declares an object of type list string : iterator, and you try to do a plus plus on this, the compiler will know it's the version, the overloaded version in this class, the list class. So yeah, so that's an important thing, that to know that this isn't just magic, that it doesn't add one to it, it does whatever plus plus means for this structure. That's an important thing to know. Now what makes this great is, if for some reason you decided you wanted to take everything that was in a list, so a list is a one directional, like you get a node and then the next one and the next one. The double-ended queue points in two directions. So you might think a double-ended queue is better than a one-way queue, right? But is there a downside to a two-way queue over a one-way queue? Well,
Memory.
well, yeah,
Memory
it takes more
references.
memory because you have more pointers. And the other thing is, like, if you insert into a double-ended queue, there's more pointers to update. You have to say, this new node is pointed to, there's two pointers that you have to update instead of one. So there's a little more work for inserting, maybe twice as much work every time you do an insert. And then traversing from left to right is really the same, because you just grab the next pointer and keep walking. So a double-ended queue gives you the flexibility of going the reverse direction, whereas a list doesn't. But so there's trade-offs. So you might think one's better than the other, but it's good to have both of them. Whatever your application makes the most sense to use, that's what you would do. But if you ever decided for some reason, let's say you made a list of things and you decided, I want to copy this over to a double-ended queue. It would be really easy to do. You create a list iterator and you create a double-ended queue iterator, and then just make the two go plus plus and copy the data over. And you don't have to worry about the logic of what's involved in the plus plus operation, because the people who made the template did it for us. All you have to know is plus plus means go to the next one, whatever that is.
So like if you mess up big time out in the real world, can you just blame it on the STL?
Well, so the STL's been around a while. If there's any bugs in the STL, someone would have hit it by now. That's what's good about this, is that it's been used by a lot of people. And if there are any bugs, they should have been fixed by now. If you ever hit a new bug, though, you write it in and they'll fix it. But hopefully they've gotten them all out of the system now. So this is, what is this? This is a list. What is this going to do now? Oh, so in this case, what this one introduced was there's a sorting method. So now, if you want to use,
Do you know the STL?
this is actually in C++, if you're going to, there's a library that has all algorithms, like sorting and shuffling and all those kinds of algorithms. You would include that in addition to including the list, and then what we can do is we can take a list and sort them, sort everything in the list. So what this code snippet does is it asks you to type in a sentence, and then it sorts the words you typed in and prints them out. And it's just one line here. You just say sort, which we're taking out of this include from algorithm, and then we're applying it to a linked list. And then, so then the thing you have to check, do what algorithms apply to what data structures. You can't just start, you can't, like you couldn't pick a Bitset and then start sorting it, because sort doesn't work on bits. So you have to see which algorithms apply to which data structures. So in this case, if we typed in a sentence, the sentence would then come out in sorted order. So, So, is there any interesting sentence that if it came out sorted would be anything interesting? So what's a sentence I should type in?
Can't think of anything.
Okay, I'll say we're at, so what would the output of this be? Now that we're calling this sort, so basically we're calling the sort routine, I'm parsing the words, putting them in a list, then I'm calling sort, and then I'm iterating through the list, printing them out. So I'm not actually deleting anything, I'm just going through them. So this should be R at Monmouth University, we. Right? Okay. So just, if you find yourself needing to sort stuff, take a whole bunch of stuff and then sort them, rather than writing a whole sorting routine, you could just call the one that they use. And I believe their version is a hybrid of quicksort and heap sort. They didn't just pick one of the standard textbook algorithms. For some reason, they decided, and they may have changed it since then. That was about 10 years ago. Yeah, quicksort, well, I don't know if you remember, heap sort was where quicksort was where you randomly pick a number and then move the lower ones to one side and the higher ones to another side. And if you picked a bad number, that pass didn't accomplish much, but if you picked a number in the middle, it would accomplish a lot. And I think they use something like, they use a heap to figure out a good pivot and then use quicksort. Some combination of the two. This ends up being useful. All of these templates end up being useful if you're doing something with a lot of data. If you're doing, if you have an array of 5 or 6 numbers, you shouldn't be using this. It's too much overkill. But if it's thousands of numbers, they hopefully pick a really good sorting algorithm. So then, okay, so then another interesting one, this will help with searching. Another interesting. Is a map. So what you can do with a map is going to basically, if you remember heap sorting or heap searching, this is where this structure comes into play. So a map basically says you declare, we're using the map template. It takes in 2 types. And what you're doing is the first type ends up being a key, like a unique field, and the second type is not a key. And the second type, you're basically saying, I am mapping the first type to something on the second type. So for example, if you wanted to do lookups, if you had a bunch of words that you read like through a book and you wanted to assign a unique number to them using I don't know if you've come across hashing, but it might come up in a data structures or an algorithms class. You assign a unique number to every word, and then you can go out to this long vector and say, for that number, give me the word that's there. So, but actually, this demonstration might point out a usefulness to it. So what I'm doing here is I am, once again, it's the same code as before. I'm typing in a sentence. I'm parsing all the words, and then every time I see a word, I put it into, so I created a map of, I'm mapping strings to integers. Strings are going to be unique, integers can be whatever I decide to do with the integer, and I'm calling it word counts. So every time I see a word, I add 1 to the word count. Adding 1 will happen to the integer, and I pass in the word. And then I parse the next word. So I just keep doing that. For every word I see, I'm going to write it to this map. So I'm mapping words to an integer. And what I'm really doing is I'm increasing the count of the integer every time I see a word. And then I'm now iterating again. So I'm actually declaring the iterator right here. I'm saying a map string to integer iterator, IT. So I'm declaring the type here. Just like in a for loop, we might say int I, or we could declare int up here and then just use I down here. Either way, I'm saying the type here, the iterator, it equals word counts is now some structure. Apparently it has order to it because it has a begin function. So I'm saying starting at the beginning, as long as I have not hit the end, keep iterating through it. And the plus plus has been overloaded for this class too. So plus plus will go, chances are this is going to be a two-dimensional array in storage, but we don't know that. We don't care how they did it, but it's probably what it should have been. And then I'm just going through the array and I'm saying, I'm printing out the second and then the first. So basically I'm counting up all the words in a sentence. So if I run this one, this is, map, let's see. Okay, so now if I run this, this is basically, I'll type in a sentence, and it'll count up how many times it saw each word. So so let's think of a sentence that has a few duplicate words, like,
Basically,
This is
you can,
This is a
dictionary,
do my cousin.
yeah, actually, it's a dictionary that's, wait,
I had to do this last.
We had to do
This
this
is
during,
during data structures.
we did this doing a single linked list pointing to a linked list. So you had like a linked list of, like which was a dictionary, and it pointed nodes that said which sentence and how many times that word appeared in the sentence. So like a linked list.
oh, okay, so that's doing more indexing of so you have
Yeah.
a paragraph and you're indexing where the words are.
Yeah, but if you use this, it does it for you like instantly.
Right, so,
Get on that, but also.
so
My cousin wrote the
What
code.
they
He
put
did
that.
this.
Was it prep the time we
You
did
did
with
this?
He was like, "Why don't you use a Hebrew
Oh,
map?"
yeah, okay,
So,
yeah.
we're not allowed. He's like, "Well, dude, I'll do it with this." And like, just look at the similarities. And like, it makes so much sense.
So what would this do? So if you had to guess, what would the output be? I'm guessing that it's not gonna sort them for us. It'll probably put them in the order it saw them. So it should say it, two, was two, the two, best one, of two,
Times
times two, worst one. So there's no guarantee, they don't guarantee the order, this is really for looking up, but I think that should be the output. Whoa, it did,
And it's
that sorted it for us, for free. I didn't ask to sort it.
Might have somewhere.
Probably did.
It's like hidden somewhere.
Here I'm reading the words and increasing the counts. Now, I'm not sorting it, so I must,
Coincidental.
That was the worst part, was sorting it.
Yeah,
huh. Well, that ends up being, that ends up,
You guys
This-
want to hand in your sign?
this ends up being a little bit of an issue because every time we add something new to the map, apparently it sorts it it puts it in sorted order. So like when the word,
That's exactly what.
Because otherwise it would be impossible for it to find half the stuff.
That's what we did. You were supposed to sort it.
Then it would have to run through the entire map
That's what I did.
to find that word again.
oh, that's a good point,
Did I do that?
that's a good point. This is, so when you declare a map, the left side is unique. The right side is anything you want to do, anything you want to say about what's on the left side. So for example, we're counting up words. The integer could be anything we want it to be, but the words have to be unique. Then every time we go to update the integer, we want to find the word, and it would make sense that it would be sorted. So yeah, they should take the time to put it in sorted order because we might be looking it up a lot, and it'll save time if it was in sorted order. So yeah, so that's the way, that makes sense. It should be sorted like that. So basically what you can do with a map, it's kind of wide open. You're mapping a unique field against another field that can be anything you want.
So you always want to have integer as the second.
No, it's whatever you want to do. Like if,
Well, how else do you?
Well, you can have int and int and count your integers. So
Or you could, no, is that like, could the thing that's not a key, the thing that's just whatever you want it to be, so, like, for example, in your dictionary thing, you had words, and then when you found a word, what did you say about it?
You increase its count in that sentence.
Okay, but let's say you wanted to say it's on, let's say when you see a word, you wanted to say it's on page 3, sentence 4. Then this thing would have to be able to contain a 3 and a 4, you know. Then you'd end up making a class with a page and a line number. Basically, it's whatever you want to do with it. So it doesn't have to be an integer. That's a good question, but these are unique things that if we go we search on these things, and we can get this thing.
Oh, okay, so
And basically, you can do whatever you want with that ability. Okay, and then another popular class is the vector class. Now, what a vector is, and I guess we could do like a coding example with a vector. What a vector is basically it's an array. So then you figure, well, if we already have if the compiler gave us an array, why have another array? So a vector is an array, but it has extra functionality to it. For example, if you wanted to insert something into a vector that's full, with an array, you have no room. You'll get an exception saying it's full. You can't insert anymore. A vector can do something nice for you, like it'll automatically double in size, copy the contents of your current vector over to the new vector, and then you'll have more room. And if it ever got so sparse, you could actually set it up to say, I want to shrink it down to a smaller vector. I don't need it to be so big anymore. And then you run into dangers where, like, if you had a vector and you had a pointer pointing at something along the way in the vector, you're in the middle of some computation, and then you decide to add one more element to it, and then it creates a new vector somewhere else and copies the contents over, and now your pointer's pointing at stale data. And you got to be careful that won't happen. So,
is there a stale data function?
no, but that would be, you'd have to have, a flag would go off saying the data's been moved, and then you'd have to know that your pointer should be reset. But there is a danger to that, or you could also, you could stop adding to your, anytime you're performing a computation that needs the data structure to stay put, don't insert, during that time. But there is a danger to using a vector. There's an advantage because it does a lot of work for you, but there's a danger to it too if you're using pointers. So that's vector's a pretty common STL template to use. And maybe we could do a programming assignment that uses that. It should be really easy then. So you could load stuff into a vector and then call sort on it and then call shuffle on it.
I wish I knew C++ last semester because all the examples that I looked up online were written in C++, not in Java. So when I saw vector, I didn't even know what the hell that meant.
Yeah, and they ended up, they called, I think, every structure out of the standard template library, I think Java used the same name. Vector, deck, list. They don't have a vector?
I don't know. We never used it before. So we talk about vectors and data structure. We
What's
still got the
their
array list. We still got arrays.
Okay,
I mean, maybe we didn't cover the whole book, but
okay.